I started to say before we had the audio situation, this is a quote I found when I was working at the very initial stages of my PhD. And I was reading through some very old Louisiana geological survey publications. They came across this quote by R.J. Russell, 1936. He was a very prominent geologist around the 20s and 30s in the state, and really came up with some of the very first information and recognition of the geologic framework, basically, of the north central Gulf Coast. And it's a long quote, but I think it's very philosophic and prophetic in many ways, where basically what he's saying is he's talking about the attack on the marshlands and the wetlands of the Mississippi River Delta and how it's created this vast accumulation of sediment that's the Mississippi River Delta at that point in time. The idea was that it had been in place for at least 65 million years, accumulating vast sediment in York on the north central Gulf Coast. And he's saying, but eventually, basically, these forces of the waves and tides are going to attack the Mississippi River Delta and eliminate it. But the only preservation of the Mississippi River Delta will really be in the accumulation of sediment that it created over those 65 million years. Anyway, I always thought it was kind of a neat quote going back to 1936 from R.J. Russell, who, as I said, was recognized as one of the preeminent geologists at the turn of the century at that point in time. So this is the title of the talk, slightly different from what I had originally suggested, trying to capitalize upon the idea of the Wizard of the Oz with sediment subsidence at sea level, oh my, sort of thing. As indicated, I'm a professor here at the University of New Orleans, been here slightly more than 25 years. First came down thinking I'd be here about 3 years, and like fishing and boating, and realized there was a lot of cool science to do here. And so here I am all these years later. I'm originally from Eastern Pennsylvania, grew up on a dairy farm. My grandfather swore that the reason I got into geology was because I was so used to picking up rocks out of the fields when we were farming and so forth. From there, I went to a small liberal arts college in central Pennsylvania called Juniata College and studied some very fundamental principles of geology. From there, I went and I did a master's degree at the University of Kentucky, looking at rock systems in central Kentucky and the bluegrass that were on the order of 450 million years old. So in terms of the age difference between what I study now, very different types of geology than what I do now. Towards the tail end of my master's degree, I was trying to figure out where I wanted to go do a PhD. Wasn't quite sure. Shortly before I finished my master's degree, a new faculty member came into the University of Kentucky, and we became friends. And he said, "Hey, there's this really big problem in Louisiana." This is going back almost 30 years, right? So it was really, at that point in time, still relatively novel in many ways. He said, "It's this big problem." I started looking into it. I realized that there was a lot of room for inquiry and investigation. I said, "I'm going to stay at the University of Kentucky and do my PhD from there." And so what I focused on specifically was subsidence of the northern Gulf Coast at that point in time. But in the process, had to really develop an understanding of the fundamental basics of geology. So since that time, since I've been here, have really focused on northern central Gulf of Mexico geology. I've worked in places all along the mid-Atlantic, all the way up into maritime Canada, South America, a little bit of Europe at different places, but really focusing on the north central Gulf. And so I'm currently chair of the Department of Earth and Environmental Sciences and also the director of the Pontchartrain Institute of Environmental Sciences on campus. So what I'm going to focus on today, like a kind of a general outline of the talk, is just a background and some problem statement about what we're faced with. Most all of you, if not all of you, are intimately familiar with some of the scary slides that I'm going to show you. But we'll talk about different components of what's going on down here, what's driving the processes of change that we see, what kind of efforts are underway to try to mitigate against that change and protect the livelihood that we have here, the importance of Southern Louisiana in terms of nationally and even internationally, I would argue in many cases, and the cost and the organization of such an effort. This is just just a very old map from 1947 by a guy named Fisk, another very prominent geologist who developed a lot of ideas about northern Gulf geology and Mississippi River Delta evolution. And basically what this map is showing is just different areas outlined here with these dashed lines of where deposition has taken place within about the last 10,000 years. So A lot of the slides that I'm going to show you today are actually slides from publications and research that has been done either by myself, students within our graduate program, or other colleagues of mine here on campus. So I try to highlight those when I can. But in general, just giving kind of background, here we are, the Mississippi River Drainage Basin covers this immense area stretching from the Rocky Mountains all the way to the Appalachian Mountains. Comes right down in here, and you can see very clearly with this situation, the Mississippi River coming down through the alluvial valley, its current path, which has altered a little bit through within this range right here, but where it's flowing right now, coming out into the Gulf. And you can see very clearly the protuberance from this perspective. I was joking with my students. I took this picture when I was in the space shuttle, and the class goes deadpan. They can't tell if I'm really serious. But anyway, you can see how the Mississippi River Delta sticks out of the Gulf, and very clearly the delineation. If the Mississippi River was not where it currently is located, we would have a straight line to coast. Okay, there would be nobody living down in this particular area. And that this entire area then is material that's been deposited and created above sea level, current sea level, in the last approximately 10 to 12,000 years. So just a general background of the Delta Plain itself in southern Louisiana. Now, in order to understand what's happening today, we have to understand some of the background of what actually built the Mississippi River Delta itself. And what we know is that the Mississippi River, for the Delta Plain as we know it today, is really built, it's composite feature. It's built of a hierarchy of different, what we call depositional units, places where the river has flowed and deposited sediment. So we look at this red area, which we refer to as a phase of fresh deposition. It dates to about 6,000 to 4,000 years ago. The river was located there. More recently, this sort of pinkish color right over here, what's referred to as the St. Bernard system, was occupied around 4,000 up to maybe about 500 years ago. And then what we know is the modern Birdfoot Delta, this blue area, occupied within about the last 800 to 1,000 years. So it's a stacked sequence of different depositional systems of sitting on top of one another because of occupation of river in different parts along the northern Gulf Coast. The important thing to keep in mind is that when one particular part of the Delta system is active and actively receiving sediment and depositing and building land, somewhere else on the Delta Plain is no longer active. It no longer is receiving sediment, and that area then no longer receiving sediment is subjected to things like wave and tide attack and potentially erosion. Right? So it's a natural process for a delta to undergo periods of active growth in one location, but land loss in another location. Okay, over the scale of thousands and thousands of years. And so what we need to understand then is how the whole Delta Plain was built through time. We also need to know then how smaller components like the modern Birdfoot Delta were built through time. And you can see pretty clearly, hopefully clearly, like right in here, there's a little area of land that's being built. This is a result of a little crevasse in the river that allows sediment to build out in this direction. And these different scales of depositional features just all collectively help to build the Delta Plain as we know it today and see southern Louisiana. So this is the scary slide, right? And all the slides I show you that show anything about whether it's an area of erosion taking place or deposition taking place, keep in mind anytime it's a hot color, a red or yellow, it's bad. It's land loss and change. Anytime there's some sort of positive, like usually bluish color, that's not so bad, okay? But this slide in particular with these colors is showing the amount of flooding that's predicted for a floodwater depth from a 100-year flood, okay, related to either flooding associated with a storm surge of a hurricane, related to during the next 50 years. And so it's 100-year flood then with level of inundation over 15 feet of covered or water on top of this part of the coastal plain and stretching pretty far inland to a minimum of about 1 to 3 feet. So large scale damages on the order of billions potentially with those kinds of floods. And that's what we're dealing with as a society and nation down here at the coastal plain. So this is a slide. This is some work that we've done here on campus. Mike Miner, currently director of the Water Institute of the Gulf Physical Sciences, a PhD student here on campus working with me. And this was a state-funded project where we were identifying how much land change is taking place at different places along the coast. So again, the red colors here indicate areas of sediment loss. The blue colors indicate areas of sediment gain. But you'll notice there's not a whole lot of blue or purple on here. It's almost all red and orange. So when we look at just this section of the coast right here with Grand Isle as reference right over here, this is along what's known as Comnon Headland. If we look at just this polygon, this area right here, for the interval 1880 to 2006, there's been this much sediment lost from that particular area. So on 10 to the negative 9 cubic meters, which is equivalent to about 285 superdomes. Okay? So large volumes of sediment gone. Carried offshore, carried maybe onshore. That'll be something that we come back to. But the point is that it's been lost. And the issue here is that when we look at a cross section, think of it like a slice of the cake, and you're looking into the side of this terrain. If we look at the cross section, this blue line right here represents what that beach profile looked like. So here would be the beach right here. Then you would walk out into the Gulf along here, and this would just slope out onto the continental shelf. This is what the profile looked like in 1880s based on data that we have. Then the red indicates the 1930s, the green 1980s, and then the data that we collected during this particular study, 2006. The point is you can see that the shoreline has translated, in this case, on the order of several kilometers land. So that's all material that's been lost and has changed the shape of what the coastal system looks like along this particular area. Okay. So this is not novel information, right? Even that Russell back in the 1930s, he also briefly identified that there were problems. People recognized that there was disappearing land. The more recent efforts to truly quantify the land loss go back to in about the basically 1950s. Louisiana Attorney General got Morgan to look at some of the rates of change. Very crude, basic maps. They were just doing little stretches of the coastline and saying, okay, in this particular area, we're going to identify based on historic maps that we have that the rate of land loss in this case is on the order of, I think that's about 16 or so feet per year. Subsequent to that, there were other studies, again, funded by the Louisiana Attorney General in like the early 70s, and then Department of Transportation, Louisiana Department of Natural Resources, Environmental Protection Agency, and then again, like the Army Corps of Engineers and Louisiana Department of Natural Resources. The point is that there's been a history of seeing that the change is taking place, and with increased data, particularly like satellite data, being able to look very closely at how the coastline looks at any one point in time compared to a previous time period, we've been able to actually refine our ability to identify specifically which stretches of the coastline are disappearing most rapidly. But we do have a history of at least being intrigued and interested in what is taking place. So this is a map from the Louisiana Master Plan, which I'll talk a little bit about at the end. And so this points out that all the reds here, the hot color again, are land loss. And so about 5,000 square kilometers since the 30s, right? And with the idea is that a future without action, which is what the Louisiana Master Plan defines as basically doing nothing alone. Then we can imagine that on the order of almost 11,000 square kilometers of land will be converted to open water within the next 50 years, right? So that would all be this land loss. Notice there is a little bit of green here at the Atchafalaya and a little bit of green here at the modern Mississippi River Delta where land is actually building. But when you look at the amount of green compared to the amount of red, it's pretty insignificant, right? So this is a really scary study that came out. This is Mike Bloom and Harry Roberts, two really prominent geologists at LSU. They came out with a study in 2009. They did some work. They were looking at essentially what the landscape might look like by the year 2100 based on our known rate of sea level rise today and the fact that the northern Gulf Coast is sinking through time. And this is the picture that they painted, right? When this came out, this really shocked everybody. Now, there are some scientific problems with their approach. They did not consider a couple elements that are kind of key, but nonetheless, I think it portends something that needs to be paid attention to. It was really great work trying to establish what the landscape would look like. So everybody knows the significance of what's going on down here. We have major port systems like Port Fourchon down on the central coast, 18% of the U.S. oil supply coming through, controlled essentially 9% of the deeper Gulf oil industry, supply ships and workers and all those sorts of things. Just the fact that the ports that we have, the fisheries, the 2 million people approximately 2 million people that live in coastal Louisiana, the overall value of the ecological systems down here, and the importance of all that, at a not only regional, state, but also national scale. So simply Highway 1 that runs down here and supplies Port Fourchon, that's the closure of that highway, if it were to be flooded on a too frequent of a basis, is estimated to be, $7 billion in costs annually because ships or because supply trains can't get down to the oil and gas industry. Simple things like I never even thought about this until just like one day, maybe like 15 or so years ago. Just the simple stuff like caterer who have to supply the offshore oil and gas industry for the guys and women who are living on platforms out can't get down Highway 1 to get those supplies in place. So big implications. So this is there's a lot of complex stuff on this slide, but it's really pretty simple. And really what I want to point out is here's what we are looking at today. This is the outline of essentially all the sediment that has been deposited by the Mississippi River Delta during the last 10,000 years. Now, the Gulf as a whole is really the process of some major events that have taken place over the last approximately 240 million years. And I'm not going to get into the details here, but there are major events that are related to the tectonics, the opening of continental plates that helped create the Gulf. Some of the major deposition that took place after the Gulf opened up, and it was a margin that was able to receive sediment. And now we have, in the last 10,000 years, the Mississippi River Delta gets locked into its current position and starts to deposit sediment over in here, meaning that the sediment we're sitting on top of is really very young compared to the overall age of the Gulf. Okay, so when we look at a cross section that comes here, again, a slice of the cake, you're looking into the side of the earth, and you look at what's going on. New Orleans would be, approximately right here. And the scale here in kilometers indicates that this is 5, 10, 15, 20. So basically, here in New Orleans, if you wanted to hit hard rock, bedrock, things like granite or metamorphic rocks of some sort, you would have to drill down on the order of about 10 kilometers, okay? Otherwise, we're sitting on top of only partially created rock, or in the upper 100 or so meters, really soft sediments, all right? So we are really, at the scale of this 10 to 15 kilometers, what's been deposited over the last 10 or 15,000 years is really this line that you can't even perceive on top of this cross-section. So we're the very thin layer of icing on a very tall cake, basically, is what it amounts to. Okay? So what we do know about southern Louisiana is that it's the apple in the basket of oranges, or the orange in the basket of apples, however you want to talk about it. Data from tide gauges, which measures the elevation of of water level change through time, shows us that it's very different. And in fact, this axis right here is what's known as relative sea level rise. This basically, we can think of that as the rise at sea level from 0 up to 1.25 centimeters per year, and then a cross section of how that varies from Texas to Florida. And so what you see is that Louisiana has these very high rates of this relative sea level rise relative to the adjacent Gulf states. And what has been identified as the primary driving factor in that elevated rate of sea level change is the fact that our land surface here is actually sinking faster than Texas and Florida and even Mississippi and Alabama. And it's part due to the nature of the fundamental geology we have below us. The subsidence here is higher because of the fundamental geologic framework underneath us at this location in southern Louisiana. Maybe just bad luck. I don't know. So I'm not going to go through all of these, but here's a block diagram of the Northern Gulf Coast. And what I'm pointing out here is that we recognize, let's see you talk to, there's some argument about this, but seven fundamental processes that are contributing to the fact that we sink faster here. Okay, and some of these are simple things, like maybe the fact that we're withdrawing fluid, both water and or hydrocarbons from the subsurface, basically pulling the water and fluids out of the subsurface. Therefore, it starts to compact and the whole surface sinks through time. There are also major tectonic events that take place, things like breaking of the continental crust, this thermal contraction. There could be instabilities at the front where material slides off the front into the Gulf, changes in salt layer at depth. I was talking to John Skinner earlier about the falling sediment compaction, that is the compression of the very young sediments. We've all walked across the beach or like through a mud or something like that. You step in mud, what happens? Your foot sinks in. That's basically, and then our situation, our analogy would be we build on top of that. Right. So, and again, major tectonic events that may be contributing to this. Yeah. So, this map here just simply shows an overall perspective. Here's Louisiana, the Gulf, Florida Peninsula, and what it's really just showing is different types of continental crust that we have identified in the subsurface below us. And the only point I want to drive here is that, again, this idea that here in southern Louisiana, the depth to what we would call like solid continental crust, granitic rocks or metamorphic rocks, igneous rocks or metamorphic rocks, is on the order of about 14 kilometers below us, okay? That tells us two things. One, we've got a long way to go until you hit what would be considered a truly stable foundation, okay? The other thing that tells us is that the Gulf has a long history of subsidence. It's taken hundreds of millions of years for it to essentially subside to create 14 kilometers of space that can be filled in by sediment of the Mississippi River Delta, that big, thick pile of sediment that I was talking about earlier. So we know that the Gulf has been subsiding for a very long time. It's what happens on continental margins. It's not just this part of North America. It's all over the globe. We see the same sort of thing on margins that where continental plates have rifted, they subside through time, and we have global history of that sort of situation. But when we look at, so those are long-term subsidence rates of the Gulf, low, almost imperceptible, and models tell us that it should still be happening, but it's happening so slowly it doesn't matter to us in terms of a daily or annual or even decadal or even centennial or even millennial scale. Okay, it just has been happening for hundreds of million years. But when we look at more recent data, some work that was done at LSU, some work that I've done, and some work that was done. This is out of Florida State University. Florida State University, I believe, was where Dixon is. Right after Katrina. These are data that show how quickly, in shorter time frames of measurement, subsidence is taking place. So this study out at LSU, they identified 0.14 centimeters per year locally based on the data they had here. And we can talk about the types of data that's used for this later on if you'd like. But they came up with 0.14 centimeters per year. So like that, okay? Doesn't seem like it much. But then there's 2 years, 3 years, 4 years, 5 years. Pretty soon in 10 years, you've got that much. Well, then in 100 years, you've got that much, right? So it does. Data here was used to identify even a shorter time frame. This is using satellite data after Katrina. And what they identified, the red here represents all the areas of New Orleans that are subsiding the fastest. And you'll notice some areas of blue that are not subsiding as quickly, but these are high areas of subsidence yellows and reds through here using satellite data. And they came up with rates of on the order of zero point 0.6 centimeters per year. So even a little bit higher than this previous study using different types of data. Again, satellite data that was used for this. So 0.6, now you're looking at that much, then that much, then that much, right? So the thing to keep in mind is these numbers seemingly initially very small, but cumulatively they add up very quickly. So science is not something new. It's been a topic of curiosity by Louisiana geologists for quite some time. Again, going back to our buddy 1936, and then the work by Harold Fisk in the 40s and 50s, and Cobb and Van Lopik in the 50s. They recognized subsidence of the delta plain as a problem. They saw things like Spanish forts that had sunken below the surface, old French pathways and roads and so forth that had subsided, old tree stumps. Even they saw some of the marshes actually disappearing. But these were all very qualitative assessments of what was going on. Simply, they were making observations. Nobody had an idea how quickly it was happening. It wasn't until we get into like 1970s and beyond where the data became available to actually begin to try to quantify. And if you're going to come up with a solution to anything, you need to be able to quantify. You need to know what the scale of the problem really is. So using different types of data, some of these folks began to make maps in different areas of subsidence. But we're still at a point going back to this quote again, R.J. Russell. You can tell I'm a fan of R.J. Russell, right? 1936. We're still at this point kind of asking, is this a regional event? Is it something that's more local in nature, just where the sediment is really thick and soft and likely to settle? Is it just because that we have these foundations on insecure or buildings on insecure foundations, or is it just the sediments compacting? And so here we are, 1936, a little bit more than 100 years later, and we're still asking some of those types of questions. My point is, we understand that it's happening. We don't necessarily have all the answers. Okay. So, what is the impact of subsidence? Well, it's not just that the land surface sinks through time and what was above water becomes below water, but it has a broader impact. So, if we look at the central part of the coast, time's not going to do that. If we look at the central part of the coast and what's known as Barataria Bay, so Mississippi River down on this side, Bayou Lafourche coming down this side, so it creates what's known as a basin, this area that's bounded by two riverine systems. When we look at this bay right here, and Grand Isle is located right down there, Fort Fushon just off the slide here. If we look at the wetland loss in here, again, the hot colors representing all the loss, in this case between 1956 and 1990, the red slide it's got a little bit of yellow there. But the red, the orange is right here, all represent the land loss in here. Okay. So when you think of maybe, okay, that just impacts this particular, what we refer to as a basin. The implications are broader than that. And the implications are things with this type of relationship. If you go back to this line, you see the basin that's bounded by like Grand Isle, Barrier Island. And there are a series of barrier islands all along the front here, fronting the bay and the basically boundary between the bay and the open Gulf. So the problem is that what happens back in the bay influences exactly what happens here too, right? They're interconnected, which is basically the way nature works in so many different ways. But wetland loss back in here increases what's referred to as a tidal prism, the amount of water that can flow in and out between the breaks between the barrier islands or the tidal inlets. And what we know, what is very well documented from tidal inlets and barrier island systems on a global basis, is that when the area back here becomes more open water, the tidal inlets have to respond to the increase in the tidal water back there. They have to allow more water to exchange through those tidal inlets. The only way to do that is for the tidal inlets to enlarge through time. So if you look at this diagram right here, it really is focused on the conceptual component of this. Here's a very small tidal prism, this black barrier area, this small blue area, and a relatively small tidal inlet. We're going to take another a larger tidal prism, a larger back barrier bay, we see an increase in the tidal inlet. And this is very well quantified, as I mentioned. Right? So what we see along the Louisiana coast as wetland loss takes place within the interior bays, back up here, for example, Barrier Bay, we can see the changes in those tidal inlets through time. So this cross section right here, now a slice through the coast. We're looking from sea level right along here to a depth of about 30 meters, right? Along the length from here, this point, west to east here. And each one of these little black areas represents the tidal inlet, basically the huge shape of what the tidal waters flow through. Okay? We always refer to this as the dripping paint, the paint dripping from the ceiling diagram, because it looks like paint dripping from the top of a ceiling. But what we see is that when you look at the 1880s and how many of these inlets existed, and how deep and wide they compared to the what is this 2006, look how much bigger they are, all these black areas. It means that what has happened is, as the wetlands have been lost in the back here, more tidal waters have to flow through those inlets between the barrier island systems. And because the tidal cycle happens within a 24-hour time period, it all has to happen. If there's increased water flowing in here, increased open area for water, that water has to still flow in and out during a 24-hour time period, which means the only way you can do that is to increase the size, the width, and the depth of these tidal inlets. And that's exactly what we see, is that these inlets, through time, have increased. Now, the problem with that, or one of them, is that as the inlets increase in size, barrier islands next to the inlets have to be reduced in size. Okay, see that this thing right here. This is something we published many years ago, actually. It shows this is the island area. So the barrier islands within this area. Basically, what is the footprint of the island? Of the islands in square kilometers, okay? And they shown in these black triangles right here. And so it's this line right here. What we'll see is that from the just before 1900s, the island area plotted here about 80 square kilometers, and we can document through all the maps and the satellite data that it has been reduced through time. So up until about 2020, the most recent data point we have, the island area increased. But look what happened to the inlet cross-sectional area. The inlet cross-sectional area is shown on this axis right here, increasing from 0 to 140 on this scale, went from here in the 1880s all the way up to here in 2000. So there's an inverse relationship is my point here. As the inlets increase, the barrier islands decrease. And the inlets are increasing because the wetland loss is taking place in the back barrier, right? So when it happens in back barrier, way back up in here is still influencing the shoreline. And it's those kind of interconnections that we really need to understand if we're going to develop effective mitigation solutions to this particular trend. Now, the other problem is we have sediment supply issues. And really the thing to focus on is what I've highlighted right here. This is some work by a guy named Kiesel, who was at LSU. I think he's retired now. But basically, he identified with all the data that was taken from the river that there has been an 80% reduction in the sediment supply in the Mississippi River since 1850. Okay? So that's sediment that is not making it to the coast to help build land and offset things like subsidence and global sea level rise. And you know well that we control the river. This is a diagram from the Army Corps of Engineers. This is the entire Mississippi River alluvial valley system. These all represent various levees and control structures that are constructed all along there. So on the order of 3,500 kilometers of levees, the result of the 1927 Great Flood, where Congress mandated and said the Army Corps has to control navigable waterways in the United States. And so levees began to be constructed. And so essentially no sediment makes it into the coastal wetlands here because levees constrict the river. Remember going all the way back to those beginning slides where I said the river has constantly been changing? It no longer is able to do that. It's locked in place. So this is a telling slide. So this is literally before Katrina, like about 6 months before, 7 months before Katrina. National Geographic, they actually came here. We worked with them. It was published shortly after Katrina. Um, there's another funny story. When I'm teaching my students and I talk about Katrina, none of them like, and they're like, when was that? I mean, I may, unless it's a non-traditional student, all the other students were maybe one or two or something like that. So anyway, so this was published right before Katrina, National Geographic. They came here. We went out in the field with them, actually. It's a nice layout. There's quite a number of mentions, as I recall, of UNO and some of the research we were doing here in this publication. But this is the picture they took and published. And it's telling me, here's this guy. He lived down on the coast. This is a picture of his camp, his family camp in the background, sitting on these pilings right there that he's in. And you can, what's really telling, when you look closely, you look behind the camp, you can see in it's like an expansive marsh back in there. And he talks in the article about having played football back there and like even, hunting deer and all that kind of stuff. And here he is in, chest high water. 2005. And then, of course, these are some of the predictions for the rate of sea level change that we expect over the next 100 years. This comes from the International Panel for Climate Change, raw meters, different scenarios, the scariest of which is like on the order of maybe almost a meter of sea level rise by the year 2100. So different scenarios. But these scenarios become important in terms of our planning for how to mitigate it against down here. And that's where we get into what we're doing down here. So this is a map showing the different projects around the state that are being undertaken to mitigate against some of the changes that have taken place. So this is actually a map. I just downloaded this yesterday. This is from the most recent, this is the most recent effort. And so basically at this point in time, there's been about $21 billion secured for trying to mitigate against these changes since these numbers are since 2007. So 35,000 acres of land, 369 miles of levee improvement, renourishing 70 some miles of barrier islands, using different fill to create marsh, and basically all the coastal parishes involved in some capacity. So here is where that map is from. This is the Louisiana master plan. This is the very first one. This came out in 2007. All right. So Katrina hits, and I don't know if you know the history of this. Katrina hits, everything's a mess, right? And basically, the state reorganized at that point in time under Governor Bobby Jindal and created what's known as the Coastal Protection and Restoration Authority to guide the coastal efforts down here. And also implemented the construction of what's known as a master plan that would be the guiding document for the state over a 5 to 6 year time frame. Originally, it was a 5 year time frame. Every 5 years, it would be updated. More recently, it was switched to a 6 year time frame. But this is the cover of the 2007 version. And the whole idea was that the master plan would create a systematic coast-wide approach to developing mitigation efforts against land loss, and not just land loss, but the whole idea of the master plan is to do these things: contribute toward land building, inland flooding reduction, and build new land or same existing land, with the idea that by doing these things, you protect communities, you also maintain the ecosystems and the natural resources that are critical to our economy and society. All the different things, with an idea that we would be looking at about a 50 billion a year sort of price tag. So the way the master plan works, if you're not familiar with it, it's extremely robust. It's really impressive. There's nothing like it on the planet, honestly, in terms of the way it's integrated to try to understand different components of what's happening on the coast and then develop these solutions. So it focuses on what's known as fundamentally an integrated compartment model, where we recognize that there are different compartments of the coast that interact with one another. So as I mentioned previously, with the barrier islands and the way they respond to the wetland loss. So we focus on how the barrier islands then may impact the wetland morphology, and how the type of wetlands may impact the type of vegetation, and then the vegetation might impact the types of natural resources like that are present, gators or different fisheries in different wetlands. how storm surges might be reduced by different types of vegetation, and then how that impacts us as communities. So it's a very integrated approach. These are all new, very robust numerical quantitative models using the best available data that we have to come up with predictions how all these different things interact, and then come up with scenarios of under these conditions, the coast will react in this way, and what can we do to prevent it from reacting that way, or what can we do to make it react a way that we think is beneficial to everybody here? So very impressive sort of approach. It focuses on three different types of efforts, either restoring parts of the coast, structural components to prevent flooding like levees, structural things like potentially buyouts, okay, of various problems that are susceptible to. So just to go through a couple different examples of what can or what has been done, we'll look at, for example, starting first at renourishment of barrier shorelines. And it's basically bringing sediment from somewhere else, putting it on a barrier shoreline and has been eroded or subjected to erosion, and recreating it. So this is some work that we've done here at UNO where we were doing what's referred to as oblique aerial imagery. You fly past Barrier Island, and then you do it again 5 years later, or maybe shorter time frame than that. We're after a renourishment project. So this is Whiskey Island, Barrier Island that sits right over here. These arrows refer to the exact same points from approximately the same flight elevation and a small single engine aircraft looking out the window, basically, up and don't drop your cap. Taking a picture before the shoreline was renourished and after it was renourished. Okay, so you can see that this inlet right here has been cut off. It's been filled in. You can even see in this picture, see these little lines right here. These are lines where they are experimenting with different directions of how to plant dune grasses to capture the most sediment. And so before and after, basically. So what does this get us? $17 million or $7 million for this particular project. And this is back in like 2000. I forget what date that was. It was like in the 2000s. Okay, so here's Whiskey Island, 1996. What it looked like. Then restoration efforts, renourishment efforts, building this in, trying to capitalize along the existing marsh there. And then 2005. This is before Katrina. All right. It's like times. Then we have to ask ourselves this question, or I think we have to ask ourselves this question. Plot of the only acreage from 1,000 to 400 starting in 1975 all the way up to 2010. So these two axes. And so here's the island acreage. You read around 900 island acres in about 1980 or so. Okay, erosion takes place. Right, we've done nothing. Here's the island acreage some years later. Hurricane Andrew hits, without plummets because of the erosion associated with a major storm. It grows a little bit. Islands do recover to an extent. And then this project, a renourishment project, takes place right here. And now the area is back up to here. So now the question I would ask is, are we projecting ourselves back to a trajectory that is starting here? And then we're starting to lose land. So we've gained some time. Have we put a Band-Aid on the bleeding, basically, right? And the question becomes, is $7.7 million worth the amount of bleeding we prevented, okay? But big hurricanes, Katrina, and we're going to take place. So somebody ripped the Band-Aid off, right? So then do we have to do the same thing, bring the island area back up to here, and now we're starting back at this point and progressively losing it. We know we're going to continue to lose it. But are we just kind of mediating the situation, a triage, if you will, on the island loss? So 26 superdomes, about $7 million. That's a small project. Here's the big project that recently took place. 2.6 million, right? Or 216 million, sorry. 60 superdomes only really happened, or a big part of it happened because of the Deepwater Horizon money that came into the system. And in this case, this is the Caminada Headland. Fushan, the main part of the Fushan port is just off the slide here. You can't see it. But basically, this whole shoreline renourished. You can see the thickness or the width of the beach right here. This is where They were renourishing when this picture was taken. They hadn't gotten past that point right there, but they still had a number of kilometers to go. But basically, dredging up material from offshore locations and bringing it on shore. In this case, that sediment was coming from 31 miles offshore. So they were dredging here, pumping it on the barges. This is the big sand shoal that sits out on the continental shelf. Dredging the sediment, putting it in a barge, pushing the barges by tugs into here, pumping it off the barges, and then putting it in pipelines and pushing it down the beach through pipelines, and then getting bulldozers and things like that to shape it to the way that we think it should be shaped. So, the question is, are these kinds of efforts sustainable? Well, once we take that sediment's gone. Okay. Now, this is a big shoal. There's still a lot of sediment out there, but we took part of it. I know. So we took it, it's gone. And so we're burning incredible amounts of fuel by doing this. Boats, bulldozers, right? And the money that's associated with it. So this is the beach. I actually took this picture. I got on the beach about 2 months after this section of the beach had been built. There was already about a 20-centimeter high scarp, meaning erosion had taken place there. Okay. Now, the beach had not equilibrated yet at that point in time. It had not become the ideal shape, but it was on its way to. So anyway, my point is that some erosion takes place. It's not like you put sediment on the beach and then all of a sudden it's miraculously healed and it stays that way indefinitely. That's not the case. Now, all I'm showing here in this particular slide is, again, going back to the limited sand sources that we have for that area. This is a cross section. So taking these are sediment cores here, and the yellow represents sand. Green represents clay. The Mississippi River Delta system is historically not a sand-rich system, so there's not a lot of sand there. If you've ever been to Grand Isle, what's the sand level? It's not like Pensacola sand, that's for sure, right? It's very fine grain. It sticks to you. You think you've gotten it off, and you're still washing it out in a shower 7 hours later. So very little sand is available. When we look along the shoreline, this is what we did here, UNO. You're looking at the deposits of where there may be sand deposits, either at the surface that could be dredged or in the shallow near surface, in the upper a couple of tens of meters. And then we have things like Ship Shoal, sitting out here. But my point is, there's very limited sand. In the 80s, when they started first looking at sand, a former UNO professor named Shea Penland did a lot of this work. They always talked about it being sand wars, because initially when they started doing some of these renourishment projects, people like EPA would say, okay, we have a little project over here, we're going to use this sand. And then Fish and Wildlife would say, well, we have a project over here. No, we're using that sand. And so it's when about the time Star Wars was out. And so anyway, they called it sand wars. So the other issue is we don't quite know where all the sediment's going in different places, right? We're learning more about it, but we don't know along the entire coast. When we place a sediment, where does it ultimately end up? And what happens on a daily basis in terms of sediment transport may be different from what happens during a hurricane. Okay, so this is a real sign I found online too, but that's not an AI-generated sign. This is years ago before AI. So we have these kinds of questions. We're still learning about some of those types of things. Also, a good example where we know more about this is the Chandler Islands, which are located in a very remote system off the east of us. This is a picture, a visual elevation model looking down the islands. This orange here represents where sediment has been deposited since the 1880s. So we do understand that there are sort of big deposits locally along the coast that where we know sediment is transported and potentially excavated here at the northern part of the Chandlers and transported down to the central part and then be redistributed. Kind of like we refer to it at one point in time, we were talking about it as like a sand gas station, basically. You know the sediment's going to end up here, so why not just transport it down here, let nature do its thing, transport it back up. Guess what project's about to take place? They are going to start using this sand up here at Hughes Point, place and rebuild what's known as part of Katrina Cut, that is a big cut in the island that's been up for quite a long time. And we know this from detailed studies, modeling studies. Basically, what this is showing, everything above this line right here means sediment is being transported to the north in this direction. Everything below this line right here means sediment is being transported to the south. So we know if we put sediment right at that point, Some's going to go that way, and some's going to go that way. So, at least in some cases, we do understand the sediment transport patterns enough to capitalize upon them and use Mother Nature to our benefit. But that's not the case for everywhere along the coast. This is a unique situation. Then we have things like marsh creation projects. This is Fushan right here down the central coast. This would be Leeville, Highway 1 running down in this direction. This is a marsh creation project that went all the way back, this is years ago, but $35 million to create these areas of marsh, dredging sediment from the open water bays. The idea that these areas of marsh creation would help benefit the local ecosystem and provide more protection. So 358 acres for about $35 million. This is a project that we were involved with at UNO. This is down in Fushan. This is a project. This was all open water before we were part of the project. We found a nearby sediment source. They pumped it into this area. They put these rocks to protect it, and then we went out and volunteers to help vegetate with tiny alternative flora and black mangrove plant in here. These are two UNO student researchers. That's actually me on the boat right there. And Greg Grandy's now charge of CPRA actually in Pike. This was a big effort. You go down to this location now; it's incredible. This entire area is full of marsh and black mangrove. So we do know it can work in some places. We have things like the contentious sediment diversions, right? So here's the Mississippi River. This is a model or a plan for different diversions. The one that's being talked about the most right now is this mid-Barataria diversion to send sediment into Barataria Bay, a monstrous project that has gone through all sorts of permitting, engineering, design, and 2 weeks ago it was put on hold. Okay? The idea was to divert sediment in through this hut, right in here in the Barataria Bay. Look at that price tag. Okay. But sending about 75,000 cubic feet per second of sediment-laden water into this bay to help build land. So that's about a hot air balloon or so. So big diversion project. But again, you have to understand where the sediment's flowing. And when it's flowing mostly in a river that I showed you earlier is mostly now devoid of sediment compared to 1850s. This is just a diagram of what it's intended to do. Here's the Mississippi River, a conduit to feed sediment-laden water into the bay. Just some details of the structure. And then these are the modeling results of what that would build. So at this location then, here's where the channel would come in. This is the bay right here. This is year 0. So this is the elevation. The colors show the elevation basically of the bay prior to the introduction of sediment. And here's what it would look like after year 10. Okay? So you can actually see a delta-like feature, but again, it is small on the scale of that wetland loss issue. All right, and that's what I always try to emphasize to my students too. But estimations of on the order of about 100,000 acres on year 2060, if it were to be implemented instantly. But again, like I said, it was literally within the last 2 weeks or so put on hold. So this is something I've always left my students with. These like 3 things, food for thought. Can we really restore the coast? I always say no. I personally hate the term restoration. Right? I think it's misleading. I go down the coast, we're working down there, and people will say, and then like I've got some good friends down the coast who have grown up down there, and like, when are you going to restore the coast? So like, we're not restoring the coast, right? When I think of restoration, I go into the family farm, barn, and find a rocking chair that my grandmother had when she was a child, and it's been sitting in the barn in the back for 60-some years, and it's got cobwebs, and the furniture is worn off, and it's broken because people piled stuff on it. I take it out, I take it in the shop, I fix it up, and when I'm done, it looks just like it did in 1932. It's restoration in my particular mind. We're not doing that with the coast. We're not taking the coast back to some point in time saying that we're going to make it look like 1970. We're not going to make it look like 2020. Right? We're going to have to deal with problems along the way as they get there. So what I do think is, can we re-engineer part of the coast? Yes. We can do that. We can mitigate the damages for particular areas of the coast that might be sustained during a flood event by creating things like levees. We can reintroduce sediment onto the barrier islands to help reduce storm surge into more inland communities. We can do some near-term protection, but again, it comes back to that Band-Aid situation. I think we're in the operating room and we're putting a Band-Aid on it, but we're not necessarily stopping all the bleeding. Yeah. And then the question of should we progressively be removing ourselves from the coast? Vital infrastructure, communities, and it's something we have to consider. And that is part, the component of the master plan is considering actually extracting ourselves partially from the coast. I'll tell you a funny story. So Katrina hit, and I lived right here in Lakeview at that point in time, had a house and got flooded. Yeah, disappeared, went up to Walker, was living in a camper, and a friend up in Walker, Louisiana. At that point in time, my former PhD advisor was president of the Geological Society of America, which is a big organization. Katrina hit in August. The annual meeting for Geological Society of America was in September, or no, October, late October in Salt Lake City. So things got settled, and he knew I'd been impacted. He got in touch and he said, "Hey, I want you to write a white paper for the Geological Society of America about the importance of coastal environments and hurricane impacts and all this kind of stuff." So myself and another colleague on campus here, Shay Penland, we wrote a white paper for the Geological Society of America, and then they invited me to come out and present at the GSA meeting in Utah in full trip. They paid for everything, and we had a special session on Katrina. We have a presentation talk about there was another special session that was underway after a talk, and there were a couple different people, like a colleague from Tulane was sitting on that panel, and then I forget where the other ones were, but there was also somebody from the Army Corps of Engineers, and so they were talking about all the impacts to the coast and all this kind of stuff. And I stood up and I said, "Do we be thinking about progressively retreating from the coast? Like a managed retreat. I'm not saying just like, telling the tell everybody that, under martial law they have to leave or anything like that, but progressively think about it." And the Army Corps of Engineers guy stood up and he said, "The Army Corps of Engineers will never retreat." I said, "Okay." So anyway, so it's three things to think about. My personal belief on some of them, or opinion, I should say. So anyway, first happy to answer any questions or try to answer any questions or discussion about anything. How about here?
I have 350 acres of land in Iowa. Well, we participated in putting up terraces, and these were in the Blue Hills.
Okay.
So we put up about 5 miles of terrace in 350 acres. So that also since 1950. We've lost, or I've lost about 3 foot of land off of the hill. Go up to the fence line, and you look into the field, and about a 3 foot drop.
So it's slumped off.
Yeah. So all this come down to make used to make
Right.
the Gulf of Mexico fill up. Now you don't get quite as much.
It's that kind of thing. I did point it out, though, one of the slides I had a little bullet, like soil conservation efforts and so forth are part of the impact, So it's like, okay, soil conservation is good, but now it impacts us down here at some capacity. And then, of course, the dams on the Arkansas and the Missouri River, the amount of dams in the country are incredible. There's a book called Damnation. How many dams are in the United States? I can guess. Something like 50,000. Yeah, it's crazy. If you look online, you can actually find it. Somebody's put a movie together of like the dam construction through time, and it's incredible. The dam construction and then how it blows up like during like some of the Roosevelt era and so forth, and the construction projects, and yeah, it's pretty fascinating. But that soil issue is a major problem, and then of course levees, like I was talking about. down here, restricting the ability during flood events that would normally naturally introduce sediment into the wetlands.
Yeah, there's a big dam on the Missouri River
Yeah,
up by Yankton, South Dakota,
exactly.
and that sucker is filled in.
Exactly. There's been talk about trying to get that sediment out of there and into the system. Yeah. But it's like peripheral talk, I think. Yeah. John, I saw you all the way back. Yes. Oh, okay. Yeah.
You showed a slide of the projects that are going on.
Yeah.
Are those all part of the master plan? And where are we with that master plan right now?
Yeah. So those are all part of the master plan. That diagram actually comes from the master plan, the most recent one. So the most recent master plan was published in 2023. Once again, unanimously approved by the Louisiana legislation. So that was 2023. And basically the way it works is as soon as one master plan gets published, and even before then, it's already work on the next one. So the next one is underway. They've increased it to 6 years. The next one will be in 2029. And so work is already underway. And what's cool about the master plan is it uses a strategy called adaptive management, which is not just inherent to the master plan. It's kind of an approach to all problem solving that's being used today, where basically you have a problem, you identify it, you come up with a solution, you monitor it, and then on the basis of that monitoring, you find out, did my approach work? And if it didn't, I modify it. And so that's the way the master plan is intended to work. Like, okay, what have we done? What have we learned? And how can we make it better? Yeah, and that's all underway right now. Yeah.
And is the only money from the Deepwater Horizon?
Sorry, what?
The only money for those projects is from Deepwater Horizon?
No, there's other money. There are other monies. Yeah, there are other monies, and I don't know all the details of all those different monies, but there are other monies. But certainly the Deepwater Horizon money it's been a big factor in some of these projects. Okay. Yeah.
One of your early slides had showed flood potentials.
Yeah.
That New Orleans and Jefferson Parish and whatever were exempt from code, and it didn't have codes in it, primarily the levee system.
Let's go back. I have to look
As to why that area wasn't in.
Yeah. Yes, would be good. Yes,
Can you repeat the question, please?
Yeah. So the question is like
Orleans and Jefferson.
like these areas here, these gray areas are not sure with floodwater depth. It's solely because of the levee system.
Yeah.
Exactly. Yeah. Yeah. So like greater metropolitan New Orleans, only because of the levee system.
Keep talking about actually being able to harvest sediment in the diversion project, which is something they've never done before. They just allow it to flow naturally, and then they go get it from the Gulf. But if there was a way of actually pulling it out right then and there, like a sieve, wasn't that part of the?
Yeah, there are different, and I don't know part of it as well, but there are definitely there are different types of structures that can be put in that capture more or less sediment during particular like flood events or low water stages in the river. And so that was one of the big questions for quite a long time. How do you optimize a sediment diversion? When do you quote turn on the spigot? Is it during a flood event or is it a low water event? And if it's a flood event, are you going to get mostly clay and fine material? Or are you going to get sand? When will you get sand? When will you get mud, clay? And so we have a pretty good handle on a lot of that aspect. It's still being studied. But yeah, there are definitely plans in place to try to optimize the volume of sediment that you get turn on, or when you turn the switch on.
A game changer if they could harvest it right then.
Yeah, exactly. Yeah. Yeah. So, and that's one of those things that just comes down to really understanding how the sediment is transported down the river, which we do have a pretty good handle on, but there's plenty to learn.
I think we have questions. One more question. Time for one more question before we probably need to wrap up today.
Sure.
So at what point is it recognized that allowing so much sediment to go down the vertifoot so close to the edge of the continental shelf is part of the problem?
Yes, because it goes down into Basically.
So is the Corps of Engineer not retreating, thinking about the fact that the Corps of Engineer is dumping the volume of sediment
Yeah.
right where we can't get at it?
Yeah. So I don't know the latest status, but when I first got here, actually, there was a project on campus we had for several years called the BUMP, the Beneficial Use of Dredge Material Program, where the idea was to make sure that any of that dredge material is being placed in a reasonable spot. That's not just being cast out and lost to the Gulf forever. There are still efforts to do that. I don't know the extent, honestly, of that right now. Yeah. Yeah. And just like that, if any of you have any questions at all or more interest in what's going on here at UNO in terms of our coastal research and programs and so forth, feel free to reach out and let us know. Yeah.
So, Dr. Kulp, thank you so much.
Sure. Yes.
I have it in my office. I will go get it. We give all of our speakers a gift of an umbrella.
Yeah.
So,
It's
amazing.
It's coming again more. So
Right. So, very, very informative presentation and questions for another hour. So,
like I said, get in touch if you have any questions or more interested in our programs as a whole. Yeah.
Tags, please, and you. Somehow.
thanks. Well, thanks for talking on. So you had heard it.
Sure.
That's not much. This is fun. Base.
Okay.
Like why is he? Yeah.
How long do you know that?